Hi, I'm Ilya, and this is my first video in the series about VLA models. In this video, we will talk about Gr00t VLA from NVIDIA. In my previous videos, I already introduced the concept of VLA and shown how these models are used to control robots, and also in details discussed some of the VLAs from physical intelligence. And now it's time to move to the other models from other companies, and Gr00t VLA from NVIDIA looks like the obvious choice. I will try not to repeat myself and mostly talk about some unique and new ideas that were introduced in this model. I will briefly talk about the history and about three versions of these models that are currently released. Then I will talk about the architecture and architecture changes between different versions. Significant part of this video will be about the techniques that NVIDIA uses to generate more data and use some non-robotics data for pre-training. And finally, we will talk about how you can fine-tune this model on your own data and how you can make it control your robot, like this one over here. Gr00t is the main VLA model from NVIDIA. And last year, they released three versions of this model. The first policy was released in March 2025, 1 year ago. It was called Gr00t N1. Then later, in June, they released Gr00t N1.5. And finally, in December last year, they released Gr00t N1.6. So you can see that they released three versions a year, and I expect them to release a new version relatively soon. There are many data sources that we need to use to understand what's happening in Gr00t, because it's like a little bit scattered. But apart from the actual code that we'll discuss in the end of the video, there are three main sources of information. Is the first official paper about Gr00t N1. And this paper describes in details how the model works, what's the overall approach, talks about data generation, about actions generation using latent actions or inverse dynamics model. It's pretty detailed. It explains a lot. It shows a lot of benchmarks and results. And definitely, if you want to know more about this model, you need to read this paper. Two other versions of the model were released without paper, and Gr00t N1.5 was released with this blog post that describes some changes that I will talk about in this video. And also it has more information. Of course, I didn't cover every detail, so I also encourage you to read this blog post and to see some examples and results that they achieved. The same is true for Gr00t N1.6. You can see different demonstrations. You can see the list of main changes that happened in this model, the description of the data used, and again, more demo and more results. So definitely read it if you're interested in the model. And before we move to the technical part, let's discuss a few kind of high-level things about this policy. First of all, it's extensively using NVIDIA ecosystem. So you may know that NVIDIA has a lot of different services that can be used for the training of different models, and a lot of services specifically for robotics. And of course, this kind of main NVIDIA VLA uses a lot of these services. So they use Isaac Sim, Isaac Lab, Omniverse, all the other simulation engines that exist there. They use a lot of NVIDIA internal models for video generation. They refer a lot to another works from NVIDIA research that are also related to the robotics and VLA, and so on and so forth. So when you learn about these models, you always in parallel read a lot about other tools, other services, other papers from NVIDIA, and this model is definitely like a part, is like very deep in this ecosystem. Second, this particular VLA relies a lot on simulated, generated, and augmented training data. And a significant part of this video will be about this video generation or training data generation for the Gr00t VLA. And finally, in many places, this model is positioned as a VLA for humanoids. And I think it's a little bit more like marketing positioning rather than technical, because of a few reasons. So first of all, of course, they trained this model on humanoids, and there are a demo where NVIDIA shows how it controls humanoid robots and so on. But First of all, they don't train it exclusively on humanoid data. They train it on many different robots, many different environments. And you will see a lot of demos also using different environments. And I fine-tuned it for my robot that don't look at all like humanoid. Technically, it's pretty generalist model, and you can use it for other types of robots too. On the other hand, all VLA models, or like most of VLA models, are positioned as generalist. So you can take other models, other generalist models, fine-tune them on humanoid robots, and they, to some extent, will control this robot. So it kind of works both ways. So I believe that Gr00t VLA and other similar models are kind of generalists enough to be able to use them for both humanoids and other form factors. Okay, now let's talk about the architecture of these models. And the architecture slightly changed between different versions. So let's start from the first one, from Gr00t N1. And as usual, VLA policy consists of two parts. The first part on the left is VLM. This part processes all the inputs. And then the second part on the right is flow matching transformer that generates the final action chunk. Let's start from the left. And NVIDIA uses Gr00t as a VLM backbone for the first version of this VLA. And this is slightly confusing, and we will see it in other versions as well, because Gr00t is a VLM from NVIDIA, and it's publicly released and open sourced. But the problem is that in this particular VLA, inside the Gr00t, this Gr00t model uses small LM2 as a LLM. But if you look at the original paper related to Gr00t release, then there is nothing about this small LM. So they don't even mention that they try to use this LLM inside this model. So it's slightly confusing because NVIDIA kind of in two different places use the same name for different models. Probably they have a lot of intersections maybe in the data that they use for training, or maybe some training recipe. I don't know these details. But the fact is that it's pretty not straightforward and confusing, and I needed to really look in the code, read many different reviews, announcements, and so on to understand what's happening. So yeah, they kind of, NVIDIA, it seems likes to call few different models by some umbrella name. And then when you go deeper, you really need to understand what used for this model. Let's go back. So just keep in mind that this is some internal NVIDIA version of Gr00t that uses small LM2 as an LLM part and siglib2 as a visual backbone. Interestingly, they frozen LLM part, but keep siglib unfrozen. It's pretty unusual because I much more often see the opposite pattern, but it is what it is. So they train this vision transformer and completely freeze LLM. And another interesting part that they don't use the whole LLM, they use only first 12 layers of this LLM. And the idea behind it is usually that if you look at the LLM, then this LLM processes data in layers. And first layers that are closest to the input usually try to kind of transform everything into some nice latent space where we can do all the kind of thinking and where we can kind of really process information. And then latest layers of the LLM, they are more overfitted for prediction of the next text token. Again, it's not exactly how it works. It's more like a high-level attempt to explain how it's happening. Overall, of course, it works end-to-end, but this is high-level idea. And based on this idea, we don't really need latest layers of the LLM because we don't need to generate any text. We just need initial layers that transform all our inputs into nice representation in some latent space. And then this representation is sent to the flow matching transformer. So flow matching transformer is connected to this VLM part. It uses normal cross attention and attends to the output of this 12 layers of LLM transformer. But this flow matching has a couple of interesting things to mention. First of all, let's talk about the state. State, I remind you, this is just a vector that contains all the positions of the motor or maybe some velocities at any point in time. This state, in case of Gr00t VLA, goes directly to flow matching transformer. In some other VLAs, it actually goes to the VLM part and is processed here. So this is kind of difference between Gr00t VLA and some other models. And I can kind of argue which one is better, but I don't have any proofs and so on. I didn't see if anybody did the proper ablation to compare it. So the arguments for using state inside the VLM is that in this case, your state and visual representation prompts, they can attend to each other and they can encode information more efficiently. But it will not kind of happen here because transformer is frozen anyway, but in general it can happen. But the argument for providing state directly to flow matching is that state and actions that are processed in this flow matching are very similar in terms of the distribution. So they came from this, they're coming from the same distribution. So the state represents the current position of the motors, actions represent future positions of the motors, and they are kind of connected. So you can consider like a state as the current state, actions as like target future states, and then it makes a lot of sense to process them together. But again, I didn't really see the ablation that compares it and tells which one is better, so it's interesting to see that there are different approaches. Another interesting thing about this flow matching transformer is that NVIDIA uses separate actions, decoders, and encoders for every embodiment, for every robot that they train their model for. And this is not, I would say, it's not surprising. It's like pretty kind of normal approach to do it. And I would probably do it myself if I need to do it from scratch. But in other VLAs, like in VLAs from Pi family, we've seen that it's not actually necessary. You can use the same encoder for all the robots. And the model is smart enough to understand what it's dealing with right now. So it's kind of, yeah, again, interesting approach. Like some companies use this approach with the same encoder. Some companies use the more like separated encoders that's supposed to be post-trained for your specific robot. I think both kind of make some sense. I don't have any opinion here. I just want to share that there are a little bit different approaches in different models. Okay, now let's talk about the next version, about N1.5. This policy uses Eagle VLM again, but the next version of it, Eagle 2.5. And I'm not 100% sure whether they use the original version released in open source, so it's again some internal version. But anyway, this version uses Qwen3 as an LLM and SIGLIB2 as an image backbone. Interestingly, they changed a little bit the freezing logic, and now visual backbone is also frozen. And they use transformer, original transformer from the LLM, but then they add extra self-attention adapter on top of it. This self-attention adapter is nothing but just few self-attention layers, and few self-attention layers is nothing but another transformer. So they basically added extra transformer on top of this transformer in order to like not train the original transformer, but train some adapter that maybe learn some extra features that may be useful for the action generation. Interesting fact about this self-attention adapter, it was very hard to actually notice that it existed because in the release, in the like blog post about N1.5, there was nothing about this adapter. And I learned that they had this adapter only from the N1.6 release, where they said that they removed this adapter. So like I learned that it existed when they announced that they're removing it. So it was another confusing moment that I faced when I was preparing for this video. Okay, and then output of this self-attention adapter again goes to the flow matching transformer. Most of this transformer is the same, except this part on the right. And this part of the right called flare. And basically, this is auxiliary loss that is very similar to Gr00t model. So you can say that Gr00t is a VLA model, but we can add a bit of the logic similar to Gr00t modeling that predicts the future state of the world, not state of the robot, but state of the world, future representation of images that robot will see after executing this action chunk. And NVIDIA says that it significantly improved the results of this VLA. I will have a section dedicated to this flare later in this video. And finally, the third version of Gr00t N1.6. Again, let's look at VLM. And here NVIDIA continued confusing me with this VLM naming, because in the official announcement they call this VLM Cosmos, and they do have this kind of series of models, the group of models that are combined under the name Cosmos. But if you look at the code, then it's called Gr00t. And Gr00t was never released as a standalone model. So maybe they just had some internal rebranding, and at some point this Eagle models, they merged into Cosmos, or maybe something else happened. I don't know. But yeah, I just need to say that all this naming of all the VLMs is very, very confusing. And also, as far as I understand, again, this is some internal version of this Cosmos VLM, not exactly the same that is released separately. So yeah, if someone from NVIDIA watching this, please can you streamline your naming of the models, because it's really confusing when you use the same name for different models. Okay, so let's look at what changed here. Not so much. So first of all, the model that is used for the backbone and for LLM, they're the same. And then they again use frozen transformer, 12 layers of it. And then they did what I already mentioned on the previous slide. So they mentioned in this release that they removed this adapter and replaced it with extra 4 layers of the transformer. As I said before, this self-attention adapter is nothing but another transformer. So instead of using another transformer on top of existing transformer, what they did, they just extended it a little bit. So they took, instead of 12 layers, they took 16 layers of the original transformer, frozen first 12, and used the rest 4 for the training. And these 4 layers, they kind of work as this trainable adapter between these frozen layers and flow matching. On the flow matching side, there were some changes in architecture. So first of all, they made it 2 times bigger, and they also changed a little bit of attention logic that is used inside this transformer. But the bigger part is that the flare part was removed. And again, it's not 100% clear whether it was removed from pre-training or not, because if you look at the code, even at the previous version and 1.5 code, there is not so much code related to flare, because flare is used during training and is not supposed to be used during fine-tuning or inference. So we could find some traces of this flare being used in the code, but not so much. But here in the next release in N1.6, they completely removed these traces. And again, it's not clear whether they completely removed the idea of flare, or they just changed the logic how it works, such as it's not needed to have any logic for the fine-tuning or inference. So I'm not sure. I think there are some questions and issues on GitHub that are also unanswered. So it's not clear whether they still use flare or not, or maybe they are moving to some other idea. But in any case, I will talk about flare in the upcoming slides, just to give you the understanding of what it is and how it works. And now let's discuss the topic that confuses a lot of people. Let's talk about the definitions of System 1 and System 2. The problem is that right now in the industry, in different papers, there are 2 common sets of definitions of System 1 and System 2. And the definitions that are used by NVIDIA are not my favorite definition, so I prefer another one. And when I say System 2 in my videos, it's not the same as System 2 in the NVIDIA papers. If you look at any VLA, more or less, or most of VLAs at least, then they consist of a couple of parts. Sometimes second part can be missing, but anyway, let's look at the ones that have both of these parts. So the first part is VLM, and the second part is some kind of action transformer. And NVIDIA, in their paper, call this setup kind of 2-system setup. They call the transformer that generates actions System 1, and they call VLM part System 2. And they say that VLM pre-trained on the internet data, and there is some thinking and reasoning happening in this VLM. And then this is fast part that generates actions, is this flow matching head. But there are a few problems with this definition. So first of all, these 2 systems are not separable. So you cannot really split them and get anything useful out of them. flow matching head needs input from VLM to make any predictions. Without this input, it cannot really generate any reasonable action chunk because it doesn't know what's happening. VLM part is not predicting anything at all. So the outputs of the VLM is just some latent space representation of the input. And yeah, they don't mean anything if they're not trained together with this action generation part. So these systems, they're not really systems. They don't like really produce any final results. And they work only when they are trained end-to-end and they are used end-to-end. So we never like use them separately. We don't run them on different frequencies. We always just make predictions together end-to-end with these two parts. So just one big neural network that kind of has two blocks, let's say, of code or parameters, and that's it. So in my opinion, they shouldn't be separated into two different systems. This is aligned with definition that, for example, used by physical intelligence, and they call the whole VLA, the whole kind of these two blocks, system one. And this system one is basically the system that generates actions based on some observations and prompt and state and something else. This is the system that generates the action chunk. And system two is something that is built on top of it. You can still reuse the same VLM, like for example, Pio5 is doing, but it's still separate system that has different goals and that has some outputs that can be used or interpreted. Usually this system 2 is responsible for planning, reasoning, correction of some mistakes, processing user inputs, using some external tools, and so on. And again, you can use the same VLM, you can use like completely separate model. For example, in case of DeepMind Gemini robotics, they have completely two different models. One model is in the cloud and uses Gemini for this reasoning, and another one is VLA that is working on the robot. They don't use, I think, this name in system 1 and system 2, but their separation is aligned with what I think is a correct definition. The idea is that these two systems, they can produce final results even if there is no other system involved. So for example, system 2 can get some input like images and some high-level task and return some step-by-step split of this task. System 1, at the same time, can get observations and prompt and actually fully control the robot and do different tasks. So when I demonstrate how my robot do some stuff, I use only system 1. And overall, a lot of this kind of system 2 are not even fully open sourced. And I didn't see yet very like nice end-to-end system 1, system 2 that is completely open sourced and that is nicely fine-tuned by some people. So it's still kind of area of active research. Saying that, as far as I understand, based on the NVIDIA demos and some presentations, they do internally have something very similar to what I call system 2 here, because they did show some demos. They do have like some reasoning model that generates some future steps and so on and so forth. But again, it's not what is released as Gr00t VLA. It's like separate thing that probably on some research stage currently. I hope it helped, and I hope you will not be confused next time when you hear different definitions of system 2. Now it's time to talk about data that is used for the training. And in most of the robotics use cases, you have this pyramid of data that consists of different parts. In the very top of this pyramid is data that is very specific for your task and very specific for your robot. And it's usually should be collected using some teleoperation of your robot. And it's very slow, it's very expensive. It means that you need to go to like the place where you want to complete this task and so on and so forth. And this data is very, very, very hard to collect at scale. In the bottom, there is this broad VLM pretraining data. Basically everything from the internet, text, images, sometimes videos, sometimes code, and so on. So all these things are usually much more easily available. And even more, you don't even need this data, because in VLAs, you usually use pre-trained VLM as your initial backbone. And this VLM is already pre-trained on this internet scale data by other companies. You don't really need to care about it. But what you need to care about is everything in between. So as I said, the best data that you need is pretty expensive and it's hard to get. So you want to have something in the middle that help you to pre-train your model on top of this broad VLM pre-training to make it more robotics oriented, to force your model to understand how everything works in the physical world, to be able to very, very quickly adapt to your new tasks and new robots when you provide a little bit data for this final fine-tuning. And different companies solve this problem differently. And in case of the NVIDIA Gr00t, they use a few sources of data. So of course, they use open robotics data. Everybody uses it, so it's not very interesting to go into it. The second one, they use simulated data. This one is interesting topic, and NVIDIA is doing a lot of things to generate simulated data. They have Isaac Sim. They have some other tools for simulation. They also have all these tools that allow you to augment your simulated data. So for example, you collect one trajectory and then simply rerun it with different augmentations when colors of all the objects in the scene are changing and different background and something else. And you can kind of generate, let's say, minutes or hours of data from few seconds recording. So they definitely use it, but again, I don't want to go too deep into this discussion in this video. And in my previous video, I talked a lot about behavior challenge and behavior data set. So this is the challenge that my team actually won a few months ago. And currently, especially in the latest version, N1.6, this data from this challenge became one of the biggest data sources for the Gr00t pre-training. So you can just go to my previous video to learn a bit more about this type of simulated data. But what I really want to discuss in this video are these two last bullet points. It's generated data and egocentric human videos. So let's go and talk about it. But before we start it, we need to discuss video generation models and word models. Video generation models and word models is a very hot topic right now, especially in the area of robotics. And there are a lot of different approaches that are trying to use this type of models to control robots directly. But they also have their place in the context of Gr00t VLA. Even so, this VLA is not a word model, it's not a video generation model. At different stages of training or data preparation, NVIDIA team uses both of them. So let's quickly just discuss the definitions and then go deeper and discuss how exactly NVIDIA uses these concepts. I think the definitions of video models and word models are a little bit blurry, but let's try to give at least some high-level definitions to understand what we're talking about. So video model is the model that takes some past or current frame and the prompt as an input and generates future video frames. I show T+1 here, but in practice, of course, you want to generate much more frames and you want to generate the whole video. Also, of course, in practice, there are some models that also generate audio. Some models can take, instead of one frame, can take more. Some models take first frame and the last frame as an input. And there are a lot of other variations, but the idea is that you kind of take current frame or current state, or sometimes don't even take it and take just prompt, and then you generate some video that's supposed to be realistic. Another type of models I want to touch are word models, and the idea is actually pretty similar but slightly different. So word models take the current state of the world and the actions and generate the next state of the world, or maybe again multiple states. The thing is that they actually have a very huge overlap, these two types of models, because video model should be word model to generate physically realistic videos because it needs to understand what will be the next state of the world. At the same time, a lot of kind of best world models are actually video world models. In this case, you just treat the state as frames as a state of the world, or at least the observations that you see about the state of the world. And also I don't know, prompt and actions are kind of similar things. So prompt is just describe what video should do in text, and actions can be some discrete vector that describes what should happen next. Again, they're very, very kind of similar. All these concepts are very aligned. All the approaches are very similar. Good video models are world models. Good world models are video models quite often. Of course, there are some exceptions. So world model also often operate in latent space, and sometimes you don't really need to generate the actual video. You just need to generate the latent representation of the future frames and future observations, and it's not acceptable for video models where your video on the pixel level should be your output. But again, there are a lot of intersections between them. The differences are more in details rather than on the high level picture. And now let's talk about it, and let's see how NVIDIA utilizes video generation models and word models in the pre-training of Gr00t VLA. One of the obvious ideas how you can try to use video generation models is to basically generate a video with your robot and use this video in training data. The idea here is that this video generation model is already pre-trained on the massive amount of videos, and it can understand the physics, it can understand how your robot works, and theoretically, if it's good enough, it will generate a reasonable video with new robot trajectories. As a small test, I decided to take a picture of my robot and try to use some models to generate a short video of my robot completing some simple task. Let's see how it goes, and let's see what you can get from existing video models without any fine-tuning, without any changes. Just a disclaimer, I didn't optimize prompt for any particular model. I didn't really try to find the better or best parameters for each model. I just uploaded everything as is, used the same prompt, used the same picture, and maybe it's not optimal for some models, so I actually didn't try to get the best possible videos. So this video are not representing the actual performance of these models. I didn't do the detailed tests, but these are just the samples of what these models can theoretically generate. Let's look at them. And you can see that this video are not perfect at all. So most of them are completely unusable, so they break the whole physics and so on. Maybe one or two was somehow close to the real physics and real robot work, but yeah, not many. Probably if you, I don't know, generate 100 videos like this, maybe a few of them will be actually good. But yeah, it's obviously not good enough, and it's not a good use of resources. So let's quickly discuss how NVIDIA decided to deal with this and how they actually use video generation model to generate extra data for the robot training. So we just discussed that generating robotics video with existing video models can be not very efficient because most of our videos will not be realistic in this case. So NVIDIA proposed alternative approach. They call it DreamGen pipeline. And you can find the code in the repo and try to run it yourself. But the idea on high level is the following. So first of all, you collect real robot video. So you don't start from scratch. You don't just use existing model. You start from the collecting a lot of video for your particular robot. And then you fine-tune the video model on this video. So you don't use the video model as is. You fine-tune it on the video of your robot. And by doing this, you teach the model to actually correctly represent the physics, or correctly represents the way how your robot works. And only then you generate new videos. And you can generate these videos in new environment. You can ask a robot to complete new tasks that are not included into the original data set that you collected and so on, and you can generate much more video, and this video will be better quality, like I hope much better quality than what I just shown, that what you can generate without any pre-training out of the box. And finally, you can apply some other model on top of it to filter out bad videos. So if video is not realistic, if it's not really doing what you wanted, you can just filter out and not use this video in the pre-training. And then you can just take all these videos, you can generate a lot of them, much more than amount of video that you collected, and use them for training. Again, if everything works, if this pipeline actually works, then in the end you'll get a lot of videos with realistic physics, with new tasks that your robot is doing. But here you can have a question. So we generate a video. Yeah, it's nice. It's good that we have a new video of robot doing some stuff. But how do we use this video? Because our model, our VLA, should predict actions. So it should know what actions our robot was receiving and executing when it was doing the stuff. And if we generate video, we don't have any actions. So what do we do in this case? And the answer is pretty straightforward. We predict these actions too. It's called inverse dynamics model. And this is the model that can take as an input 2 frames, let's say frame n and frame n plus h, where h is our horizon. And then by giving this initial state and the final state, it can predict what was the action chunk that moved our robot from the state on the left to the state of the right. And by this moment, we already have a lot of video of our robot that we collected to fine-tune the video model. And when we collect this video, we can also collect all the actions as in any robotics data set. And then we can use this video to train this model. So again, using the trajectories, real trajectories, where we teleoperate our robot, we can collect this data and then use this data to train the model that takes initial position or initial picture of the robot and the final picture, and then predicts the action chunks that we need to apply to the initial frame to go to the final frame. This model will predict action chunks the same as VLA, but this task is much, much easier because VLA knows only the current state and some final target, and needs to predict some optimal actions to complete the target. But this model, it already knows where it will end up. So it knows where it is right now. It knows where it will be like in 1 second, and it just need to predict what you should do to move to do this like 1 second movement. So this model is much, much more straightforward than the VLA itself. And yes, you can train it. You can train it on the same data that we already collected, and then simply apply it to a new generated video. So let's say our new generated video is a video of a robot that trying to put this ball into the cup. And we trained it on some other tasks in the past. And now we can simply take these 2 frames, apply our model, and we will get predicted action chunk. And we now can use this action chunk as the target for our VLA when we train our VLA on this generated video. Of course, all these things, they work only when you have a high quality data and high quality models. So from my experience, all the time when you use some artificial generated data, it works only when the quality of your generated data is very, very high. And second, when this generated data actually adds any extra knowledge. If you train your video generation model only on your own data that you use for the robot training, then there will be no new information in this video generation model. But if you have already some video generation model that is pre-trained on like thousands and thousands and thousands of different video, and specifically robotics video, then you can apply some kind of distillation by generating this video of your robot doing some particular task. So again, I think it's not so straightforward and not so easy to make it work, but it's pretty interesting approach how to generate more data. You can find more details on the official DreamGen page and also read the paper and use the code on GitHub. They provide a good explanation of what they're doing, and also a lot of demo. You can see that they're also not perfect, but they're much better than what I generated with these out-of-the-box models. So it's definitely better approach than just generate videos from models that are not suitable for this. And yeah, you can see different demo, you can see the results, you can see more details about this approach, and you can try to use it. So yeah, we discussed that teleoperation can be pretty expensive because we need to use the real robot. So what are other alternatives? And the obvious alternative, if you want to develop robots that can do the task that human do, we can collect data from human. So what we can do, we can just record some video where human completes some task and use it for training. I think that the thing that everybody kind of dreaming about is to be able to train robots on kind of any type of human video. So I don't know, I can show you right now how to do some task, and then the robot can watch this video and learn how to do this task maybe even better. Of course, it's not really working exactly like this right now, but what's already working pretty well and was mentioned in multiple papers and shown that it actually can improve the results of pre-training and even post-training of the VLAs is a human egocentric video. So what is egocentric video? It's a video in which human kind of have cameras, let's say like this, on their head, like I'm wearing right now. And then they simply do some task and they behave like they are basically a robot. So imagine it. So if you trained a model and this model already trained on like 100 different robots, then when we add a video with a human doing some task with the hands, then basically for the model it's just another type of robot. And the model can learn from this video as well as from other videos of other robots that are used in pre-training. So let's look right now on the video from this camera just to understand how it works and what this video look like when they are recorded. Okay, so let's say that we found people who are wearing this camera and complete some tasks, and we collected this egocentric data set. But what's next? Yes, so our goal is to be able to train our model on this data. We have video, good, but now we need actions. And you can remember that in the case of the robot, when we generated robotics data, we had some initial data set with actual robot teleoperation, and we could train the model that simply takes one frame and another frame and predicts the actions that needed to move from one frame to another. But the problem with human video that there is no actions. Yes, so we don't have any like discrete actions that we are following as human. One approach would be to try to maybe, I don't know, detect all the fingers and all the joint position on the arms and try to transform it into the actions. And yeah, it's also like valid approach, and I've seen some people doing it. But what NVIDIA is using to use this data for the Gr00t pretraining is different. So they use approach that is called LAPA or LAPA, not sure how it's pronounced. But the idea of this approach is that instead of predicting the actual actions, we predict latent actions. So if we don't really have already some actions for our robot or for the human, let's try to create some discrete latent space that contains these actions. So what we do, first of all, we have first part of the model that is very similar to what we've seen before. It takes two images and encodes it into some latent action space. But now we need to somehow force this vector that we generated to be something that we can interpret as actions. And to do it, we have a second part, that is decoder. So encoder simply transforms the two frames, current and future, into the vector. Then we take this vector and combine it with the same original frame and train another model that can reproduce or reconstruct the future frame. So the goal of this model, of the second model, is basically to predict this future frame based on the current frame and the vector that we provided. And if you think about it, that this is exactly the definition of action. So if this vector explains what we need to do with this state to move to this state, then this vector is nothing but some actions. Another interesting observation, then this part on the right is actually a world model. So we have a current state, we have actions, and we predict future state. Eventually, what we do, we use kind of the full world model as a loss to predict these latent actions for our current video. And when we train it end to end, and we kind of compare this reconstructed frame with the original future frame, and train it in such a way that eventually this image is as close to this image as possible. And again, I will not go into details. It's just much easier to show it as some images. But I think there are many different approaches how you can do it. And I think you can do it in latent space. Also, I don't go into details how exactly they use this encoder-decoder. I think they use VQ variational after encoder. So basically, these latent actions are not continuous. They are discrete. Eventually, they also try to interpret some of the sections, and they realize that, okay, some action actually means to move right hand to the left. And this action was kind of the same for robots and for humans. That is nice. And also, NVIDIA tried to apply the same approach for robots, for which they had actually targets. And they compared the performance of this approach versus performance of previous approach that we discussed, where we directly predict the known actions. And sometimes, depending on how much data you have, one of these approaches can be better or worse. In the low data regime, this one can be even winning approach. If you have a lot of data, then you can train directly on your robotics data. Overall, it's very, very interesting approach. So you kind of create some discrete latent actions, and then some of them are even interpretable, and you do it through kind of world modeling as a loss. It's pretty nice approach. The authors of this method shared the paper, the code, and the blog post about it. So you can read it. You can find much more details than what I explained. And you can try to use it using the code provided in the repository. Okay, so we touched the term world model already. But now let's look at how they use auxiliary loss world model in the actual VLA pretraining. So first of all, this is the same schema as I shown on the previous slides, just a little bit in different colors, and VLM part is squeezed into just one block because it's not important here. And this action transformer is shown as many layers. So this is VLM as before. This is our action transformer that is just a transformer with many layers and cross attention to VLM. And it receives some noisy actions and predicts flow matching velocity that allows us to denoise the inputs that we have and eventually generate the actions. So what NVIDIA did in this flare work, they used the same transformer to predict extra objective. And this objective is basically the latent representation of the future observations. So they didn't change the weights. They didn't change anything in these layers. They just added extra inputs along with noisy actions. And then they took the latent representation, internal representation of these input vectors from one of the internal layers of the transformer and use this representation to predict the future observations. And then they simply took the future observations, then passed them through some backbone, and simply compare what is this latent representation of the future observation versus what the model predicted, and use it as additional loss that is used to train this transformer. So again, they don't really change anything in weights. It's still the same transformer, just more inputs. And interesting thing that they use some intermediate level. So why don't they use the last level? They use some layer from the middle of the transformer, and the logic is following. So first of all, you need to give model some capacity to make good predictions. So this is why you don't take anything from the first layers. You kind of need at least few layers for model to make some predictions. And this is why you need kind of to go deeper to get better predictions for this extra loss. But the problem is that these two things, noisy actions and flare embeddings and like future representation, they're from very different distributions. And as they share weights with each other, if we will take these predictions from the last layer, it means that we force this transformer on every layer to simultaneously predict two very, very different distributions, and it can actually hurt the predictions of the flow matching velocity. But when you take this representation from some layer in the middle, or like maybe close to the end but not the last one, it means that the last few layers are actually exclusively used for the noisy actions, and yeah, whatever happened here doesn't actually impact the loss. So model in these last few layers at least can focus on kind of making predictions in the correct format from the correct distribution that are important for the actions denoising. So yeah, this idea of taking something from the middle kind of helps to train all these layers, but at the same time, it doesn't hurt these predictions. In their paper, they said that it really helped a lot for the pre-training, and especially when you use some extra data like egocentric human data and so on. But again, it's a little bit of mystery whether they're still using it or not, whether they removed it from N1.6 or not, because yeah, they didn't comment it, but they kind of removed it from the code, so it's completely not clear. But anyway, I think it's a very nice idea. I think they're having this VLA model as an auxiliary loss is a kind of nice thing, because if you think about it, predicting correct actions and predicting what will be result of these actions are kind of very, very interconnected tasks, and there can be a lot of cross-learning between them. One maybe last thing to mention is that I called it VLA model, but it's not exactly VLA model, yes, because according to the definition that I gave before in this video, VLA model should accept actions as an input. But in this case, the input that this model has is noisy actions. So it doesn't really know for sure what actions will be applied. It knows only this noisy version of the sections. So I would call it, I don't know, quasi-VLA model in this case, but still it's like very, very similar in terms of overall idea. Gr00t VLA uses Flare, but actually Flare is a separate paper. So it has this blog post that has a lot of demo, and unfortunately the code on GitHub is still not available, but still you can read through this, you can look at the demo, you can look at some explanations and find more information and more results of testing and demo of how the actual human egocentric video can help to train robots. I wanted to keep this part of the video a bit high level and more like encouraging and overall educational rather than go deep into technical details. So I didn't really explain step by step exactly what NVIDIA did. I just tried to show you some high level picture and just demonstrate overall ideas and approaches that they used. If you want to go deeper, then I encourage you to read all the papers that describe these approaches and try to use it on your own data, or try to use it in your own model training. And again, there will be a lot of small technical details that will probably impact the result significantly. And even so, NVIDIA shares a lot of code and a lot of papers related to it in GitHub. It's not like 100% clear what exactly they used for the training of this particular model. So yeah, this is why I didn't try to actually reproduce it step by step in all the details. But again, if you like these ideas, if you want to try them, there are a lot of examples for many of them in the NVIDIA repositories. You just can go and try to use it yourself. And yeah, and I did this slide with like a few quotes from different papers and blog posts just to give you a sense how much compute NVIDIA actually used to train this model. So for example, they used 1024 GPUs for this model and 50 1,000 H100 GPU hours for pre-training. In like another place, they talk about generation of video, and they say that they used 105,000 L40 GPU hours on 3,600 GPUs. And finally, for N1.5, they trained the model again on 1,000 H100 GPUs with a very huge batch size of more than 16,000. So yeah, just to give you a sense how much data and how much compute you need to pre-train this kind of VLA models. But of course, if you want to fine-tune your model, you don't need so much. I will show you how to fine-tune it on just one GPU in a couple of hours. But yeah, the pre-training, the initial pre-training is really, really expensive and compute-consuming thing. As usual, just for demonstration purposes, I fine-tuned this model to control my robot over here. This is the modified version of LAPA. And in one of my previous videos, I shown the dataset collection part and explain what dataset I use for this testing. And it's like very simple one task dataset that contains just 15 minutes of video recordings of me operating this robot. And now let's quickly go through the code, discuss how you can fine-tune the robot at home, and also look at the demonstration of how it works with my robot right here. And this is the main Gr00t VLA repo. And this repo contains all the code that you need for fine-tuning and the evaluation of the model. There are a lot of guides. There are a lot of already pre-trained models that you can just test on different environments. And of course, there is like explanation of quick start of what you need to do. And it's pretty straightforward. So you just install the library, you take your data set that should be saved in the robot format. You need to slightly change some things in data set, but they're more on the metadata level. So there is nothing hard, just add one small file there. And finally, you can simply run training. And in basically a couple of hours, you can fine-tune model on a simple small data set. Of course, if you have a huge data set, if you have a complex task, if you have multitask and so on, it will take much more time. But my simple demo data set took maybe a couple of hours to actually fine-tune. So it's pretty fast. And again, you also have code for inference here. Yeah, this repository has everything you need, but also I created a couple of helper scripts that help me with inference on my particular robot. And I will also share them and provide you a link if you need it. They even have this page for 700. So if you have one of them at home, it's pretty straightforward. You can follow it and train your model and run it on your robot. As usual, there is an alternative. You can train the model using Gr00t, but as far as I can see, they only have Gr00t N1.5 and don't really have the latest version available in Gr00t. But I haven't tried to train any of the Gr00t models using Gr00t library. But anyway, I guess they will update it at some point in the future, and you'll able to use this Gr00t library directly as well. Now let's go back to the official Gr00t repository and quickly go through the fine-tuning logic and how to do it. As I said, it's pretty straightforward, so they have all the guides. First of all, you need to prepare your data, and it uses the standard Gr00t format. The only thing that changed, you need to add this modalities config. It's basically just lists all your inputs and outputs and like match it with the model. And then you need to create this modality JSON in your dataset repository. And again, it's very straightforward. It simply, in my case, lists all the joins, all the states, all the actions that I have on my robot, and provide the names for the video inputs and some annotation. And it kind of reflects what you configured in this file for fine-tuning. After you've done it, everything is ready, and you simply run the fine-tuning script with the path to your dataset and some parameters for the training. If you're training on some single task, small dataset, then again, like a couple of hours will be enough for your model to actually start performing pretty well. And then when your model is trained, you can evaluate it. So they provide some example how to do open loop evaluation, but it's not exactly what we want. We want to apply our policy to the real robot. And to do this, they have this serving script. this script basically loads your trained policy and creates a server on like this port that can make predictions. You send observations from your robot to this server and you get back the predicted action chunk. Depending on what robot you're using, you probably will need to create some connector between this server and the robot. I provide one example. So this is the script based on the, again, examples provided in the Gr00t libraries. And yeah, there are a lot of helper functions, but basically what my script is doing, it's connecting to the policy server, and then it's connecting to the robot, and then simply runs the loop where it gets observations from the robot, make predictions using the policy server, and then send these predictions one by one to the robot. Yeah, saying that, this script is very simple and straightforward. I literally just vibe coded it one shot. It's not so hard, but I would say it's not optimal. It kind of creates this intermediary between your robot and policy. You probably can make it much more optimal if you directly run the policy and send the actions directly to Lukivi. I think you can do it. It's not hard at all. Just, again, need to match format of input and output, and basically that's it. Everything else already provided by either Gr00t or LRobot libraries. So again, you'll need some adjustments for your robot. You will need some connector, but it's very, very easy to create. And now let's look at the actual rollout. So here you can see how my robot completes this task. So currently the robot itself controlled by Raspberry. On the same Raspberry, I'm running this Lukivi server and also this connector that I just described. And the actual policy is running on another computer with GPU. And every prediction takes around 160 milliseconds in my case. But because I have some overhead for the sending data back and forth, then it takes almost 2 times more. So it takes around 300 milliseconds, and as I said, it can be optimized. So your robot can move a bit more smooth than you can see right now in this video. But overall, if you look at the performance, it's actually pretty good. So in this video, you can see completely uninterrupted session, and it's can complete the task many times before it makes the first mistake. Let's actually speed it up a little bit and watch a few more rollouts. The robot was trained with this green cap and orange ball, so it didn't see any other data during the training. And also the prompt is about the green cap and orange ball. But surprisingly, it's pretty robust to changes in colors. So when I put completely different colors objects in front of it, it still understands what needs to be done. Even so, this cap is actually orange, like original ball in the training data. But you can see that it still eventually starts to make some mistakes. But to be honest, I'm not sure if it's good or bad. So it shows that, yes, it generalizes to slightly different objects, but at the same time, it shows that it completely ignores the prompt. Policy simply learned to drop the ball and put it to the cap. It didn't really learn to follow the instructions that I provide. But again, as I say in all my videos about VLAs, if you want to achieve this multitask performance, text prompt generalization, and so on, you need much more data. So when you start to train your policy or fine-tune your policy on hundreds of hours of diverse data, then yes, you will see some generalization and some language following. But if you just want to test it and fine-tune the simple problem, don't expect that it will be generalist policy. Don't expect it to do anything outside of the training data. This is everything I wanted to discuss today. I think overall Gr00t VLA is very interesting model. They use a lot of unusual ideas, especially in the area of data generation and using these word models and video models to improve VLAs. So I think these ideas are pretty interesting. They also, as I said, actively using all the NVIDIA stack. So when you read about it, when you try to understand how it works, you also learn about other parts of the NVIDIA ecosystem. That is also pretty interesting thing to do. And of course, they are moving like pretty fast. Again, in last year, they released 3 versions. I'm pretty sure they will release one more version pretty soon. And I hope that this model will keep improving and improving. So overall, yeah, keep following it, keep watching, keep reading about the updates. So yeah, let's see what NVIDIA is preparing next. And thank you for watching. I hope you really enjoyed it. Please like, subscribe, share this video if you think it's interesting. Also, I read all the comments and I try to answer, or I try to incorporate the answer for questions in the following videos. So if you have any questions, don't hesitate to ask me in the comments. And see you in the next video. Bye.